Yeah, thanks so much for the invitation. So my name is Thijs. I'm a postdoc at the AI group in Wageningen University. And yeah, it's great to be here. And I've already met a few people we only met online before, so that's really nice. And I'm going to use Alexi's talk as a great segue into how can we explain deep SDMs. And so, of course, deep SDMs don't need an introduction, but I just want to say that SDMs kind of have, I think, a dual purpose. One is to map distributions, but the other purpose is to understand the environmental drivers of species occurrence. And of course, deep SDMs have the potential to improve the mapping of the distributions, but often because the models are more complex, that comes at a cost of interpretability. And so the question is, can we explain deep SDMs and kind of get the best of both worlds? And yeah, I want to highlight not just because you're the organizer of the conference, but because I think it's a great paper. Like Robin's paper focus on what I would call attribution-based explainability. So that's like attributing the predictive performance to the covariates or modalities that go into the model. And I will motivate this in a little bit, but sorry, what we focus on is concept-based explainability. But I want to start with a study that we've done about 2 years ago, and then we'll move into how we are trying to explain these models now. And this is based on the UK BMS dataset, so the UK Butterfly Monitoring Scheme dataset, which is an amazing dataset it's a monitoring program that's been going on for, I think, over 50 years, where trained volunteers walk the same transect route every week, and there's a very standardized protocol to count all day butterflies on that route. And so there's more and more locations that are added every year typically. And the data, most of the data is available on GBIF with a delay of a couple of years. And so we used data from 2 years, and then after some filtering, we ended up with a data set of just over 1,300 locations. The exact route is not revealed on GBIF, but it's obscured to a 2 by 2 kilometer grid. So the goal is to predict from this 2 by 2 kilometer area the species distributions of 62 different species. And our curated data set is we also make this separately available on Zenodo. And so when we started this, we kind of followed the approach from the Sedberg paper, where we trained a convolutional neural net to predict the 62 species from Sentinel-2 images. And the data set is quite small. So with these 1,300 data points, we use about 1,000 data points for training the network. And obviously this quite limits the performance that we can get. So when we look at for example, our main metric is the mean squared error, and so when we compare against the baseline, these are just numbers, right? But we get this performance of 1.2 compared to 1.4 at the baseline, and it's hard to know exactly where the ceiling is because obviously it's impossible to predict it 100% accurately in this task. But we would certainly like to improve it. And so. One thing that would for sure improve the model is if we would have many, many more locations, but that's of course not feasible at all. It's already, I think, one of the biggest citizen science projects in the UK for ecological data. So one thing we tried at the time is to see if we can also learn from the similarity between the locations because the data is really high quality. So it's good presence-absence data. So what we did is to essentially introduce an inductive bias to the model and to add a supervised contrastive learning objective to the loss function. And so the intuition is that we want locations with similar species. We want that for locations with similar species, that the image encoder also creates embeddings that are similar. And so by using this to create a contrastive loss, we add it as a regularizer, which slightly improves the performance. But then the next thing we would like to do is to say, okay, can we use more input data per location? So, a greater variety of data modalities. And so for this, we use Earth embedding models. So I'm sure many of you are familiar, but essentially Earth embedding models take different remote sensing modalities and using self-supervised learning extract this embedding. And it's kind of great for two reasons. One is that it combines a lot of different modalities, so there's more information than just the single Sentinel-2 image that we had before. But secondly, it essentially takes care of the pre-processing that normally makes it very difficult to use different satellite data. And there's kind of two classes of Earth embeddings. So one, what we call implicit representations, so that's that learn to map coordinates to an embedding, and secondly, explicit representations that take data attached to a coordinate and map it to a representation. And so we tested a few different models. And so we found that already implicit models outperformed the model based on Sentinel-2 data, so using setclip and geoclip. And the explicit models of Earth and Tessera significantly improved the performance. And one thing that was interesting that we found, and I'm curious if anyone else has any experience here, is that when we consider these areas, if we use Alpha over Tessera data, which is at the same resolution of the, yes?
Alpha is trains on GBIF though, right? So.
Yeah, I think this.
This is something I've just been really struggling with recently. They use the GBIF observations as part of the training. So if we use it to do SDM, aren't we data poison?
Yeah, it's a good point. So I'm not sure. I thought they used the to correct me if I'm wrong, I thought they used GBIF data for trees occurrences, but do you think they?
I think they use.
They do
it. All species. Okay.
No.
And they don't play the stores.
Yeah, exactly.
Okay, I was not aware of this.
It's not
Okay.
necessarily legal because
Yeah. Sure.
We all love the non-commercial use.
they're being very public about it.
Okay.
Anyway, so this is something I've been thinking about.
Yeah,
When
that's a
we're
good
doing
point.
SDMs,
Yeah.
can we or can we not?
Yeah.
It depends if your test set it is in JBIF or not. If your test set is not in JBIF, then that's not
GBIF, but the locations, other species data that is in GBIF, isn't it a bit?
It's a knowledge. It is.
Yeah, I mean, it's not the exact data set, but it's a representative and correlative data set. Anyway,
That's okay. Yeah, thank you. Yeah. Yeah, that's a great point. Well, something else I wanted to bring up is that so because those data are at the same resolution of the original satellite data, we need to do some kind of pooling to efficiently handle the data. And so we tried different ways of pooling, also training like convolutional nets, for example. But in the end, what worked best is just to average all the pixels in a location and get an average embedding, which is kind of surprising. But maybe that's also an artifact because of the small size of a data set. But surely there's a better way than average pooling. So I think that would also be very interesting to further explore. So coming back to explainability, so it's great that we can improve this benchmark performance using embeddings, but we do lose even more kind of the inherent interpretability that we would normally have from satellite images. So if we could normally, maybe via GradCam or something, attribute certain areas in an image or features of an image that contribute to a prediction, once we change to using Earth embeddings, it's even attribution-based methods don't work well anymore if this is our only modality, right? So we gain performance, but we lose interpretability. And so what we would like is to instead of attribution-based explainability, to develop concept-based explainability. And with that, what I mean is that we want to kind of be able to read out from kind of bottleneck in the network, what are the relevant concepts that led to this prediction. And I made this slide, and then last night I realized this is not, I think this is in English I've read admirable butterfly. I don't think they're particularly correlated to mud banks, but the idea is can we somehow use language to query what's in these embeddings and attribute that to the prediction. And if that works well, then we can also use language to query for other things.
I guess if it's this, right, and you end up with something that makes no sense ecologically, then you know your model's working.
Exactly. Yeah, exactly. So that's, I think in the ideal scenario, we can use it to explain the predictions, but also explain why predictions don't work, or use it as a way to calibrate when predictions are reliable and when they're not. And so quickly, our approach is so the kind of the setup we have so far, but kind of presented in this more extensive way, is that we have this EO data, which is encoded to an embedding, and then we train a prediction head on top of the embedding to predict the species distributions. And now we try to language align it using like a CLIP-style network. And so what we create are text captions for each location that are embedded through text encoder, and then with a contrastive loss, we try to language align these existing like Earth embedding spaces. And kind of a reasoning here is that there's some work on this, but often the captions that are used for remote sensing data are quite like colloquial. So they will say something like, stunning scenery with a lake next to a forest or something, which often, because they've been generated through a VLM in the first place. But because here we're interested really in these like very fine-grained ecological types of information, we generate these captions using existing geospatial data. So if we already have data on climate variables or land cover or these, the things that we know influence species distributions, we can convert these to captions. So a caption might be something like, this is 80% wooded area with this much precipitation, blah, blah, blah. And maybe we can change these to something more colloquial. So saying something that's mainly forested, adjacent to rough pasture lands and high amount of rainfall. So we generate captions in this way, but the captions we try to base them as much as possible in this real geospatial data. So they're not generated by an LLM, but by like fixed templates that use geospatial data. And then once this model is aligned, we can create new captions and embed them, and then create a similarity to all the locations using the EO embeddings. And then finally, we can combine this with like a RAG setup that creates these captions that need to be queried. So let me start by some examples. So we're kind of in the process of training these models now. So I'm sure we will be able to get better performance soon. But what we have right now is, for example, after we train the model, then for like the test set of locations, we can query locations using concepts. So for example, here we've created a caption that says water bodies such as lakes, rivers, and sea. And then we embed that text and compute the similarity against all locations, and then rank the locations by the similarity. And these are the top 5 locations in our test data set. And clearly these are all on the coastline. So so that's worked well. Here's another example for the caption densely populated area with many houses. And I hope it's not too dark, but here you can see there's 4 areas with quite a lot of urban areas. And then interestingly, the best matching image doesn't have any urban area at all, but has this kind of moorland that I think looks a bit similar to urban areas, but it's hard to say. And then as a final example, to kind of test precipitation, we have a caption that says wet area with a lot of rainfall. But again, it just retrieved all these coastlines, right? So clearly the alignment here is a bit misaligned. Maybe there's more rain on the coast, but clearly there's a kind of linguistic misalignment. And so we can quantify this by comparing the ranking of the similarity to the ranking of the actual geospatial data that we have, right? So we can compare the precipitation against the similarity with this precipitation caption. And in this way, we can, a bit as mentioned before, we can kind of quantify like what parts of the, like what kinds of information are well aligned and what parts are not well aligned. And so So here I'm showing results for two models, so Alpha Earth and GeoClip. Like generally Alpha Earth performs better on most types of information, but for example, on this precipitation, GeoClip, even though the performance is fairly low, GeoClip performs a bit better, which I think makes sense according to the types of like the type of information that implicit encoders are thought to encode. Okay, so that's the language alignment and kind of trying to quantify what parts are well aligned and what parts are not well aligned. And then we can use existing information to get out habitat information. So, for example, from butterfly conservation in the UK, they've created these very nice 2 pages for a lot of butterflies on what good habitat looks like. And so using an LLM, we parse this into small captions. And we ask an LLM to write these captions in a way that they could be inferred from remote sensing data. And then in the context, we give the scores of all these similarity assessments and let them rank the captions by things that, or filter the captions by aspects that are well aligned and ignore things that are not well aligned. Yeah, so some examples for this butterfly would be, so captions would be, yeah, pretty short stuff like broadleaf deciduous woodland dominated by oak with open canopy structure, etc. Yeah, and then we embed these captions and just to validate it, and we can then correlate the how well locations score on these captions and what the actual species occurrence probability is. And this is for 15 different species showing the correlation. So generally, most correlations are positive, meaning there's a there's a positive correlation between what what linguistic information is in the embeddings and how that relates to the predictions. And also, it's higher for the predicted labels than for the actual labels, which makes sense, right? So it's closer to the belief of the model, even if that belief is wrong. Okay, and that's all I wanted to show. So just to conclude, I think explainability is very critical for the impact of DeepSDMs. And for example, these Earth embeddings really improve predictive performance, but they require some kind of concept-based explainability, I think, to be useful. Which you try to do here through this language aligned with geospatial data, and quantifying the scope of like what is well aligned and what is not well aligned is very important. And and for us, kind of the big picture is seeing, okay, once this works well, can we then also query, like essentially use the capabilities of the language model and the language embedding space to query features that we don't have geospatial data on, to really get to information about habitat condition, etc. With that, I would like to thank you very much for listening and thank our collaborators, and especially Gabriel, who is a research engineer in our lab, who's done a lot of the work. Thanks.
Short on time, so maybe 1 or 2 brief questions if you have some. Maybe everyone is welcome. So students are welcome to ask questions. Please.
Do you think the image quality matters? Not even image quality, but sometimes can be dark, sometimes can be very bright to influence the query.
The image quality of the satellite image.
Yeah.
Well, so in this case, when we use these Earth embeddings data, we no longer use the satellite images.
Okay.
And it's one of the reasons to use these embeddings, because we know the image quality can vary a lot.
Okay.
We've actually looked at that, like systematically probing for like an image at the same place with different quality, what the text similarity is, and it changes a ton. So certainly that's reasonable.
The Earth embeddings, I was wondering if you also, like, obviously you didn't show it here, but if you compared it just to a model with like just simple bioclimatic variables, because I've seen in a lot of examples where a satellite image on its own doesn't work as well as just bioclimatic variables on its own. So I was just wondering, especially with the comparison with the Earth, like the geofindustry models,
Yeah, it's a great question. So to be honest, we haven't done this for this use case, but we use the same model for a few other use cases. For example, on detecting they're called urban heat islands, so areas in cities that heat, and there we have done these baselines, and generally embeddings always outperform like regression on covariates.